Good morning all my dear student. So in today's lecture we will see UV visible spectroscopy. This one it is our second lecture of spectroscopy. In previous lecture we learned what is that spectroscopy, what is that electromagnetic radiation and types of spectroscopy. So here now in this lecture we have to see UV visible spectroscopy. Yes, this UV radiation, this region, it extends from 10 nanometer to 400 nanometer. Then the visible radiation, that region, it starts from 400 nanometer to 800 nanometer. This UV region, again it is subdivided into two parts. First one, it is near UV region, that is from 200 to 400 nanometer. Far UV region, it is below 200 nanometer. For far UV region, we have to use some different spectrophotometer, and this it is studied under vacuum condition. Common solvent for both this near and far UV region, common solvent it is used ethyl alcohol, or in some cases it is used hexane. Now, whether it is UV or visible spectroscopy, some electronic transitions are there. Which are these electronic transitions and why these electronic transitions are there? When light, either visible or UV, this it is absorbed by valence electrons, outer electrons. What will happen? These electrons are promoted from their ground state to higher energy state. That is, they are excited from ground state to excited state. And because of this excitation, this spectroscopy, it is also called as electronic spectroscopy. Now, if any organic molecule is there, it contains three types of electrons: sigma electron, pi electrons and non-bonding electron. Now first, sigma electron. Any saturated compound is there, so in that there is sigma electron. Like saturated hydrocarbon is there, it contains carbon hydrogen bond, carbon carbon bond, carbon oxygen bond, it can be carbon sulfur bond, so it contains that sigma electron. Then the second type, what is that second type? Second type it is pi electrons. Pi electrons are in unsaturated organic molecule, and these electrons form double or triple bond. Like this, it can be carbon carbon double bond, carbon carbon triple bond, or carbon 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 nitrogen triple bond, carbon oxygen double bond. So wherever there is the double or triple bond, so it contains pi electrons. Then the third type of electrons are non-bonding electrons. That is, it contains lone pair of electrons, and this lone pair, it is not involved in any bonding. So for example, that can be ROH. So O contain oxygen, oxygen contain lone pair. RNH2, so that nitrogen, it contain that lone pair of electron, and this lone pair of oxygen and nitrogen, it is not involved in bonding of that carbon to hydrogen or carbon to nitrogen. Now, after these three types of electrons, now we will see types of electronic transitions. Electronic transitions means whenever that electron, it will jump from bonding orbital to antibonding orbital. So any organic molecule, whenever it will absorb energy from UV or visible region, electrons from its bonding orbital or non-bonding orbital, it will jump from that bonding or a non-bonding orbital to antibonding orbital. Bonding orbitals are sigma and pi orbitals. Non-bonding orbitals are n level, and antibonding orbitals are sigma star and pi star. Now theoretically, 6 types of electronic transitions are there. Which are these 6 electronic transitions? Sigma to sigma star. So any organic molecule, if it will contain sigma electron, so whenever it will absorb that UV visible radiation, it will jump from sigma to sigma star, or it can jump from sigma to pi star. if that organic molecule will contain pi or pi electrons, so that will jump from pi to pi star, or it can jump from pi to sigma star. Then if it will contain antibonding electrons, so that will jump from n to sigma star, n to pi star. Now out of these 6 electronic transitions, only 4 type of transitions are practically possible and 2 transitions are forbidden. Which are these 2 forbidden transitions? Sigma to pi star and pi to sigma star. So 4 type of transitions are only possible. Which are these 4 transitions? Sigma to sigma star, pi to pi star, n to sigma star and n to pi star. Now we will see its diagram. So relative energies for excitations, so that we can see here, energy for sigma to sigma star, it require more than that of energy required for pi to pi star, than that of energy required for n to sigma star, than that of energy required for n to pi star. And this it is clear from this diagram also. So all these transitions, 4 transitions are shown in this diagram: sigma to sigma star, pi to pi star, n to pi star and n to sigma star. Now in which molecule which type of transitions are there, so that we have to see. Out of 4 transitions, now we will see first one, that is sigma to sigma star transition of electron. These transitions occur in compounds in which all the electrons are involved in single bonds and there are no lone pair of electron. Where this type of arrangement it is possible? This type of arrangement it is possible in saturated hydrocarbon. Now single bonds are usually too high in excitation energy for most instruments. Now this type of arrangement, that is saturated hydrocarbon, where can we see? We can see that in alkane family like methane, ethane, propane. For methane, its lambda max it is at 125 nanometer. For ethane, it is at 135 nanometer. So here we can see that this it is in far UV region, that is below 200 nanometer. For this we will need special type of spectrophotometer, and there in that special type of spectrophotometer we can see the transitions. Which transition we can see? We can see only sigma to sigma star transition. So this it is rare spectrophotometer and we can use it for only saturated hydrocarbon. So the next one possible transition it is pi to pi star transition. Where this type of transition it is possible? Wherever there is presence of pi electron. Pi electrons are present in double bond or triple bond. Now this transition again it is divided into 3 types. First type is where that first type of transition it is possible where there is presence of single double bond, like in ethene only one double bond is there, or this it is possible in if 2 double bonds are there, these 2 double bonds are isolated double bond. Lambda max of that it is in the range of 160 to 175 nanometer. These types of bands are called as E bands. Where this one it is possible, we will see example. First example it is ethene, CH2 double bond CH2. So there is only one, and that is pi to pi star transition. In second example, that is 1,6-octadiene, there also this type of transition it is possible. 2 double bonds are there, but these 2 double bonds are not conjugated. These 2 double bonds are isolated from each other. So its lambda max it can be below than that of 175 nanometer. This again it comes in far UV region. So we can't use here our normal spectrophotometer. We have to use this special type of spectrophotometer. Now the second type of pi to pi star transition. Where this type of transition it is possible, where there is presence of more than one double bond, first condition, and second condition it is these two double bonds, means at least that two double bonds should be conjugated. We know what is that conjugation. Conjugation it is alternate single and double bond. Here the absorption maximum it is 210 to 280 nanometer. So for this we can use our normal spectrophotometer. This type of band it is called as K band. Okay, now we will see two examples for that. For that K band, first example it is butadiene. Which butadiene it is there? That is 1,3-butadiene. So here the arrangement it is alternate single and double bond. Then these two bonds are in between carbon carbon. Second example it is of mesetyl oxide. Here also these two double bonds are alternate single and double bond, and these two double bonds are in between carbon carbon, and second double bond it is in between carbon and oxygen. So here the diagram it is shown for that ethene and butadiene. So what is the difference in between that absorption? So here it is for ethene only one pi to pi star transition it is shown. In butadiene as there is presence of two double bonds, so two pi to pi star transitions are shown. Again this K band where it is possible, where there is the presence of more than one double bond and at least two double bonds are conjugated. So this one it is the K band and it comes under 210 to 280 nanometer. Now third type of pi to pi star transition it is B bands. Now this B band it is because of benzene and its various compounds, it will show broad band containing peaks in fine structure in the range of 220 to 270 nanometer. So these types of bands are possible if there is benzene type of structure is there. So here in pi to pi star transition, three types of bands are there. Which are these three types? First one it is E band. E band it is for 160 to 175 nanometer. Where this type of bands are there, where there is the isolated double bond or single double bond. Then the second band it is K band. K band it is 210 to 280 nanometer. Where it is possible, where there is presence of more than one double bond and there is presence of conjugation. In the last one it is B band, and B band it is 220 to 270 nanometer. Where it is possible if there is presence of some benzene type of structure is there. Okay, now third type of transition, possible transition that we have to see, and the third type of possible transition it is N to pi star transition. This transition it is shown by unsaturated molecule having atoms like oxygen, nitrogen, halogen, and these bands are weak bands and its absorption maxima it is 270 to 320 nanometer. Again, now where this type of transition it is possible, first condition there is presence of some heteroatom, and that heteroatom it is having some lone pair of electron. So that can be oxygen, nitrogen, any halogen it can be. That is first condition. Second condition it is there should be presence of double bond in between that carbon and that of heteroatom. So that is, it can be, first example it can be C double bond O. So that we can see that C double bond O in aldehydes, we can see that in ketones also. So here its absorption maxima it can be in between, it can change somewhat, but it can be in between 270 to 320 nanometer. So example it is aldehydes and ketones with some conjugated double bond. If it is, then its that absorption maxima it will change from 320 to something 300 and 350 nanometer. Again I will repeat this one. So here where it this type of transition it is possible, two conditions are there. First condition it is there should be presence of some heteroatom, and that second condition it is that heteroatom it is joined to carbon with double bond. Now here, if aldehyde or ketone if it is there, then we can see two transitions. In one that we can see two transitions, and these two transitions are pi to pi star, as pi bond it is there, and then the n to pi star, because there is presence of that hetero atom. So relative energies for excitations, so that we can see here, energy for sigma to sigma star, it require more than that of energy required for pi to pi star, than that of energy required for n to sigma star, than that of energy required for n to pi star. And this it is clear from this diagram also. So all these transitions, four transitions are shown in this diagram: sigma to sigma star, pi to pi star, n to pi star, and n to sigma star. Now, in which molecule, which type of transitions are there? So that we have to see. After these four transitions, now we'll see some examples. Like first one is CH3 single bond, CH3 single bond, CH3. So here there is presence of only sigma bonds. So here only sigma to sigma star transitions are possible. Then the second one is CH2 double bond, CH2. Here the first, it will be sigma to sigma star for that first single bond, and then as there is the isolated double bond, so here the pi to pi star transition is there. Then the third one is CH2 double bond CH, single bond CH double bond O, that is aldehyde. So here three transitions are possible. Which are these three transitions? For single bond, sigma to sigma star, then for that double bond, two double bonds, and that two double bonds are conjugated double bond. So for that pi to pi star, and then for that C double bond O, there will be N to pi star transition. Then this one it is ethanol. In ethanol there is first one it is sigma to sigma star, and the second transition it is N to sigma star, as there is presence of that oxygen with lone pair, and this it is joined to carbon with single bond. So there is the presence of that second transition, it is N to sigma star. Next one is benzene. Benzene, here there is presence of two type of transition, that is sigma to sigma star for all single bonds, and then pi to pi star for all double bonds. CH3 C double bond, sorry, CH3, sorry, this one it is acetic acid. So for acetic acid for all single bonds, this one it is sigma to sigma star, pi to pi star, and as there is presence of that heteroatom with lone pair of electron, so here there is the N to pi star transition. We have to see some terms which are regularly used in that UV visible spectroscopy. Two terms, main terms are there. First one it is chromophore. What is that chromophore? Chromophore is a functional group. And what it contains? That functional group, it contains a multiple bond. That multiple bond, because of that multiple bond, its lambda max, it will be above 200 nanometer. So which type of transitions are there? Because of that multiple bond, there can be transitions like pi to pi star transition and or N to pi star transition. So because of that pi to pi star or N to pi star transition, it absorbs in UV region, and that is above 200 nanometer. So what is its definition? Definition is chromophore is a functional group containing multiple bond capable of absorbing radiations above 200 due to pi to pi star transition and or n to pi star transition. Now we will see examples. Like first one, it is ethene, CH2 double bond CH2. So here there is sigma to sigma star and pi to pi star transition. That pi to pi star transition, it will be at 171 nanometer. Its lambda max, it is 171 nanometer. Second example, it is CH3CO CH3. This one, it is our ketone. So here all other transitions are there, like sigma to sigma star transition is there, and second transition, it is n to pi star transition. This it is its lambda max, it is 279 nanometer. So this one, it is our chromophore. Now second term which we are using, and that is oxochrome. What is that oxochrome? Oxochrome, it is saturated group, but with that saturation it contains some lone pair of electron, so it will contain some heteroatom. Because of that saturation, because of presence of sigma bond, this it will not absorb in UV visible region, but when it is attached to chromophore, which will contain some multiple bond, so its wavelength, means that lambda max, and its intensity of its absorption, it will change. Now again I will repeat this one. What is that oxochrome? Oxochrome itself, it will not absorb in UV region, but whenever it is attached to our chromophore, it will change its lambda max, it will change the intensity of its absorption. Now we'll see one example of that. Like first one, this one, it is benzene. Benzene it is chromophore, because it is having some functional group, so it is having some multiple bond. Second, it is this one, it is with that benzene OH, it is attached. Now if we will see that OH only, that OH, it is with saturation, it is with lone pair of electron. That single OH, it will not absorb in that UV region, but whenever it will attach to that benzene, then its lambda max, it will be 270 nanometer. Same it is with third one, NH2, it is with saturation, it is with lone pair of electron. It will not absorb in that UV visible range, but whenever it will attach to our chromophore, that is benzene, so its lambda max, it will be 280 nanometer. So first one, it is benzene. Benzene, it is only chromophore. Its lambda max, it is 255 nanometer. But when oxochrome, it is attached to benzene, so this one, it is our, its lambda max, it will change. It will change from 255 to 270 nanometer. Then in third example, NH2, it is attached to benzene. So here lambda max, it will change from 255 to 280 nanometer. First one, it is benzene. Second one, it is our phenol. Third one, it is our aniline. After these two terms, now we have to see some effects. Four effects are there. Whenever any substituent it is added on chromophore. What is chromophore? Chromophore, it is a functional group with some multiple bond. So if any substituent it is added to that chromophore, then what will happen? Four effects, or these are called as four shifts. Which are these four shifts? First shift, it is bethochromic shift. It is also called as red shift. Now what is that red shift? Whenever any substituent it is added to that chromophore, its basic lambda max, it will shift from shorter wavelength to longer wavelength. This it is effect of substituent. So this it is nothing but the lower energy. What is that second shift? Second shift, it is hypsochromic shift. It is also called as blue shift. Whenever any substituent it is added to that chromophore, its lambda max, it will shift from longer wavelength to shorter wavelength, that is higher energy. Or the third effect, third shift is there, and that third shift is hyperchromic shift. What will happen here? Because of that substituent, there will be increase in intensity of absorption. Hypochromic shift, because of substituent, there will be decrease in intensity of absorption. So in short, that four shifts we can see in this graph. So here from 200 to 700 nanometer, this one it is intensity of absorption versus the wavelength. The bathochromic shift, it is towards longer wavelength. Hypsochromic shift, it is towards shorter wavelength. And hyperchromic and hypochromic shift. Hyperchromic, there is increase in intensity of absorption, and hypochromic shift, it is there is decrease in intensity of absorption because of chromophore. Now where that effect it will be and how it will affect, so that we will see in next slide. Now here one by one we will see that shifts or that effect. So first effect or first shift, it is bathochromic shift. What is that bathochromic shift? This it is when absorption maxima, that is lambda max. So that lambda max of any compound, because of that substituent, it will shift to longer wavelength. This it is called as bathochromic or red shift. Now this happens due to presence of an oxochrome, that is any substituent, or it can happen because of any solvent also. So here it can be because of presence of OH, NH2 on benzene ring. So because of that, its lambda max, it increases from shorter to longer wavelength. We already see that in our previous example when I explain you that oxochrome. In that, in first benzene, then the second example it is of phenol, third one it is of aniline. So in benzene, its lambda max it is 255 nanometer. But when OH it is substituted there or NH2 it is substituted there, then it shifts from 255 to 265, or this it increases from shorter wavelength to longer wavelength. So this it is because of presence of oxochrome, or it can be because of some solvent effect. So for that we can see the next example. Here in first, that paranitrophenol, this paranitrophenol, its lambda max it is 255 nanometer. If we will change the solvent, like we will change the alkaline medium, because of that alkaline medium, now what will happen? There will be formation of phenoxide ion, that is there is presence of negative charge on that oxygen. Because of this negative charge, it will increase the delocalization, that is conjugating structure, it will number of conjugating structure it will increase, and because of that conjugation, what will happen? Its lambda max it will change from 255 to 265, and this it is nothing but the from shorter to longer wavelength. So this it is nothing but the bathochromic shift. In paranitrophenol, this it is 255, but if we will change the solvent, number of conjugating structures will increase, and because of that, there will be red shift, that is from shorter wavelength to longer wavelength. So this shift, it is because of two reasons. One reason it is presence of oxochrome, like we saw that in benzene, phenol and aniline. So there is the effect of presence of oxochrome. And the second reason or second condition, it can be because of solvent effect. So for a solvent effect, we saw this one example of paranitrophenol and phenoxide ion. So there change in the solvent, shorter to longer wavelength, that is red shift. Now we have to see the next shift. Next shift, it is just opposite. This one shift, it is just opposite to our red shift. What is that blue shift? Blue shift it is when absorption maxima, that is lambda max, of any compound, it shifts to shorter wavelength. It is called as hypsochromic shift, or it is also called as blue shift. Now this, it is just opposite to that red shift. So what can be the reason for this blue shift? Just opposite to that red shift. This, it happens due to loss of conjugation, or it can be because of the solvent effect. Number of conjugating structures, if it will decrease, because of that what can happen? There can be blue shift, that is from longer wavelength to shorter wavelength. So for that we will see one example. Like for aniline, its lambda max it is 280. But if we will change the medium, if we will change the medium to acidic medium, so here in acidic medium, that NH2 group, it gets protonated, and because of that it results in loss of conjugation. Number of conjugating structures will decrease. Because of that, now this, it is its lambda max, it will change from 280 to 265. So that lone pair of electron, it was available in aniline for the conjugation, but now in that whenever the medium it is changed, so in that what will happen? That lone pair now it is occupied. This, it is not available for the conjugation. Because of that, now there will be the blue shift, that is from longer wavelength to shorter wavelength, from 280 to 265. So this, it is also one effect of substituent. Now third and fourth shift. What is that third shift? Third shift, it is hyperchromic shift. What is that hyperchromic shift? Here only we have to see what is that. This, it is intensity of absorption maxima. So this intensity of absorption maxima, if it will increase, it is called as hyperchromic shift. And this, it is because of introduction of any oxochrome. So this, it is like our red shift. Reasons are same as that of red shift. So this, one more example in that we can see, and that is pyridine. Pyridine, its lambda max it is 257 nanometer, and its intensity it is 2750. But if methyl group if it will introduce in that pyridine, so here what will happen? So because of that oxochrome, now intensity of absorption, it will increase from 2750 to 3560. So it is same as that of our red shift. Then the fourth and last one shift, it is hypochromic shift. Here when intensity of absorption maxima of a compound, it decreases, this, it is called as hypochromic shift. When it will happen? If there is some distortion in its geometry, or some number of conjugating structures, if it will decrease. So this, it is same as that of our blue shift. Only here the effect, it will be in intensity of absorption maxima, and if it will decrease. So here one example we can see here in first, that is naphthalene. Naphthalene, it is 19,000. This one it is its intensity of absorption. But if methyl group it will introduce there, because of that methyl group there is some distortion in its geometry. Because of that, the intensity of absorption, it will decrease from 19,000 to only 10,250. So this, it is same as that of blue shift. In red shift and blue shift, the effect, it is in their wavelength, that is from shorter to longer or longer to shorter wavelength. But in hyperchromic and hypochromic shift, there is the effect in its intensity of absorption. After these four transitions, now we will see some examples. Like first one is CH3 single bond CH3 single bond CH3. So here there is presence of only sigma bonds. So here only sigma to sigma star transitions are possible. Then the second one is CH2 double bond CH2. Here the first, it will be sigma to sigma star for that first single bond, and then as there is the isolated double bond, so here the pi to pi star transition is there. Then the third one is CH2 double bond CH, single bond CH double bond O, that is aldehyde. So here three transitions are possible. Which are these three transitions? For single bond sigma to sigma star, then for that double bond two double bonds, and that two double bonds are conjugated double bond. So for that pi to pi star, and then for that C double bond O, there will be N to pi star transition. Then this one it is ethanol. In ethanol there is first one it is sigma to sigma star, and the second transition it is N to sigma star, as there is presence of that oxygen with lone pair, and this it is joined to carbon with single bond. So there is the presence of that second transition, it is N to sigma star. Next one is benzene. Benzene, here there is presence of two type of transition, that is sigma to sigma star for all single bonds, and then pi to pi star for all double bonds. CH3 C double bond, sorry CH3, sorry this one it is acetic acid. So for acetic acid for all single bonds, this one it is sigma to sigma star, pi to pi star, and as there is presence of that heteroatom with. So for today this one it is sufficient. Thank you.